And there we go. Okay. So, let me get to the census system first, so I can do that and not have the registrar yell at me. Everybody's here. And Jack, hopefully you were on Twitch this morning. If you could type something in the Twitch chat, that would be great. And then I'll know you're here. Yep, Jack, you're here. Excellent. Okay, so that's everybody. So I can mark you all present. All right, so let me start by taking questions from the Brookshear stuff, and I fixed the document that had the broken link at the very end, so it should be good now. Yeah, Evan. Oh, yeah, sure. Okay. So, yeah, so all I meant there for using Genie um, is there's nothing special about Genie, right? I mean, for this you could use Microsoft Word if you wanted. Um, all I meant there was let me just make a new file and let me just call this say oops. The percent just for a comment like usual. Let's see, Jack. Let me make sure I can see the Twitch chat. Oh, it looks like somebody named Reaper's Revenge is here. Who could that be? Yeah. All right. So um, the let me get my coffee and sit somewhere. Huh? Well, I've got Twitch on my other laptop. Yeah, and this is sorry. I the coffee hasn't kicked in yet this morning. So, okay. So there's nothing special about Genie for the purposes of the Brookshear stuff. Okay. All I wanted you guys to do was to get used to doing things on the Pi and using Genie so that when we start doing ARM assembly where it's more important to use it, and then it will be useful. Okay, so for example, obviously we can't do this with Brookshear stuff, but um, the build and run, these sort of buttons up here will configure to do automatically do some of the stuff that um, we need to do with the ARM assembly, and they won't do anything right now, obviously, because Brookshire is made up. But okay, so let's say, for example, that we wanted to, I don't know, what's a simple program in Brookshire we could write? Okay, so let's start with load, uh, and we're going to load FE into register, say one, did you say? Okay, so it'd be one. Okay, yeah, so what's the difference between why does this keep blinking? Okay, I'm not sure why this keeps blinking on and off on the stream. That's somewhat annoying. Um, okay, so what's the difference in this language between a dollar sign and the hash mark? Yeah, go ahead, Porter. Louder. Yeah, but backwards, right? So dollar sign refers to the contents of a memory cell, okay? And hash mark refers to the actual value of whatever specified, okay? So the two different examples, so if I had, for example, or two different things, if I had that and that, these two load operations are going to be doing different things. The first one is going to load register one with the actual numerical value FE. The second one is going to load it with whatever is in memory cell FE. Okay, good. Hmm? What do you mean? Well, okay, and so this is the difference between assembly, right, and machine code. In assembly, the only way you know the difference between the two different types of load operations is the hash versus the $sign. The mnemonic for the operation is load in both instances, okay? But in machine code, when we translate this down, what is yes, Jack, R1 is the same as 1. What is loading an immediate value in machine code would be, that's memory. Yeah, 2 is immediate. Yeah, yeah, so this would be 2-1 FE, and then this one is a machine operation would be 1-2 FE, right? So the difference between, and I used a word there, so when you're loading a specific value, that's often called loading an immediate, um, and or a load immediate type operation. We'll use that word quite a bit more specifically with the ARM architecture. And then the other one is loading from whatever is in memory cell FE. Its contents, who knows what they are, it's just whatever's out there, okay? Yes, okay, so this is the sort of thing that it would look like. Or if you want, for example, I think in my examples, what I really ended up doing was, for example, putting in a memory address. I wrote it sort of like this. Okay, so this is called an assembly listing, um, and what you've got running down the left, of course, are the memory addresses for each of the instructions. And for this particular architecture, they'll always go up by 2s because each instruction takes 2 bytes to specify. Okay, following that is the actual instruction, and then to the right we've got the actual what the assembly is, and then to the right of that would be whatever comments you want to put in, which could be text or anything to kind of help you write it. Uh, Now, as I think we saw last time, you don't necessarily know what the memory addresses are going to be until after you're finished writing the program, right? Because you don't know how long it's going to end up being, and you might have to, move some things around, like a chunk of code, 2 chunks of code. You might have to switch where they are or whatever, and that's obviously going to affect the memory addresses of where they're located in the end. And so when you're writing it, you don't really have to put the memory addresses there until you're very, very finished. Um, did space influence the code? No, because um, so the thing with Brookshear, to actually make this run, what do we have to do? To actually execute this, what do we got to do? Yeah, we got to put it in the emulator, right? And there's no automated process to do that yet because I still haven't gotten around to it. Okay, so we have to basically take this thing and take the 2-1-FE, 1-2-FE, and then I should put a halt command in here, right? Uh, and actually load that stuff into Joel's emulator to execute it. There's no automated way to do that yet, okay, because I haven't written the software to do it. And so because of that, the spaces are not relevant here. Um, the only reason I put the space in the way I did was just to make it more readable, right? That's all. Yeah. Okay, so is that part okay? And then let me put in a halt command just for um, there. Okay, so what would be my my string of code when it's all done? It'd be 21FE, 12FE, C000, and then all I would do is take this, copy it, go to Joel's emulator, and then once Chromium loads, okay. Okay, here, and then if you go to the URL and you put in a hash mark, and then you, there it goes, and then paste the string afterwards, and then reload it, it will have everything there in memory for you. So you don't have to type it into each individual memory cell. That's kind of convenient, right? But like I said, one of these days I'll get around to writing an interpreter that will, or an assembler that will take the source that we had in Genie, magically process it, and then bam, pop open a URL to Joel's emulator with everything loaded. Okay. Well, actually, what I think I'd be more likely to do is to fork his project on GitHub and just build in everything to the website so it's all in one spot. But that might actually be more useful, because then everything would be web-based and it'd be sort of a one-stop shop. Okay, so then we could execute this code and not much would happen, but you know, that's it. Okay, so that's all I meant by using Genie, right? And then just for my sanity, all you guys are going to do when I said the link is, after you've got the stuff loaded in and you've made sure it works, you copy that link and you put it down here, so that all I have to do is copy paste a link and it loads in your code for me, and then I can check and make sure that it actually runs okay. Yeah. ASM. And that's it. Yep. So so here I've got my source. I'll say file, save as, and I'll just call it whatever .asm. No. No, on Linux in particular, a lot of things are not preset the way you might expect. Mhm. Yeah, yeah. And in fact, you know, so for example, here where I've got this C file, you see how it's highlighted things in a particular way, right? Well, look down here at the bottom. When I saved it as a .c file, it said, oh, this must be C source code. And so I'm going to highlight the syntax according to C syntax highlighting. .java, it would do the same thing. Okay, but with Java syntax, obviously. Um, and if we save it as .asm, so like for example, I've already got a different file open, ASM file, right? So I've got some stuff here. You notice down there it says file type ASM. Um, so there are lots and lots of different assembly languages. I think this one is defaulting to Intel assembly, which means that you see how add is kind of highlighted, but some of the other ones aren't, right? Well, add and sub and mul are instructions, or the mnemonic for instructions in the Intel architectures also, and STP and some stuff like that are not. It's called something different. And so this thing is doing syntax highlighting for the wrong kind of assembly. And I don't know if anybody has written a ARM64 like language definition that you could load into this. I know in Atom, which is another text editor that I like to use on the Mac, you can load in some packages that'll do that. The only problem with Atom is I haven't yet managed to get it working on a Raspberry Pi, because some of the back-end stuff it uses doesn't have ARM64 hasn't been compiled for ARM64. I've tried building it from the source, but it keeps breaking, and I haven't figured it out yet. So that's okay. Genie is perfectly good, and in some senses actually better because the build commands are configurable. But whatever. Um, yeah. So that's all I meant. Now, one thing, since you asked about the file extension, I want to make clear the difference between ASM as an extension and .s as an extension. They're both assembly, right? So there's no difference in terms of what you see uh, between the two of them. So why are we going to use two different extensions for this for what's basically the same stuff? It's a convention, but what is the convention and why am I doing it? It's a very good reason. Exactly. So if I write the assembly by hand, I'm going to use .asm. If I have something that I've written in higher level code like C or whatever, and I have the machine produce the assembly for me, I'm going to use .s. They're both assembly files, okay? But the reason I'm going to do that is for twofold. One, it means it's very easy for me to tell what I wrote and what the machine wrote. Um, and it means that if, for example, like this C program here, right? So I wrote this simple C file, and then I had the machine generate that assembly file. Well, maybe I would go through and say, all right, I've got this little program here. I'm going to manually write that in assembly myself. And then I'm going to have two versions of it, the version I wrote and the version the machine wrote. And by using different file extensions, I won't accidentally overwrite one of them with the other. Okay, so yeah, so that's the only distinction there. I mean, there's, like I said, there's nothing special about the two file extensions, but this way we can keep straight what's machine produced versus what's human produced. Okay, so yeah, so your programs that you guys are going to turn in, right, for the Brookshear stuff anyway, are basically going to look like this, right? So you'll have, you know, your code and do put in this stuff here, the memory address and the actual machine. That's the last step you do, right? Because you don't know what the addresses are going to be, and there's no point in translating each instruction into machine code until you're finished, right? So do that part last, and then the very, very last thing is, of course, this step here, okay, to load it into the emulator. And all that's going to do, obviously, is check to make sure that it actually works. So, yeah. Good? Okay. What other questions do you guys have about the Brookshire stuff? Okay. It should be, of course, mostly ringing bells, especially those of you who took 101 with me at some point, right? For the rest of you, well, I guess you're just doomed. No, I'm kidding. Yeah. I mean, it's not too bad, right? In 101, it was probably like, what on earth is all this stuff? And now it's like, oh, well, I mean, but you guys have been through 111 and 211 by this point, most of you. So, well, you've been doing more programming since then. So, you were a wee lad in 101 just a year or two ago. So, yeah. Um, okay, so question, preguntas, fragen. Yeah, 2112. Uh, oh, right. Okay. So how you decode it, right? So in the first command, 21FE, what type of operation are we doing? We're loading an immediate value into a register. That's opcode 2. Which register are we putting it in? register 1. What thing are we loading? FE, okay? In the second command, what's the operation type that we're doing? We're loading from a memory cell, which is operation type 1. Which register are we going into? Register 2. What memory cell are we coming out of? FE, right? So the $ and the hash mark are the only way that we can tell as humans between on the assembly. But the machine, I mean, $ hash, those mean nothing to it, right? It's literally all just ones and zeros, and so that's the distinction, is the opcode is a 2 versus a 1. And how do you know which opcode's which? Well, the table in my little my notes document has them all listed, right? There is no opcode 0 on this architecture. Opcode 3 is to store something out to memory, and then so on and so on, right? Followed, what's the last one? Opcode C, which is the halt command, okay? So what that means actually is that there are 4 unused opcodes. Opcode 0, D, and E, D, E, and F. So if we wanted to actually extend this architecture, we've got room to do it. Yeah, and in fact, I know what some of my extensions would be. So why was it, the very last example that's in that document is the Fibonacci program, okay? And you may have noticed that that program is particularly sneaky because it modifies its own code, okay, in a certain spot. The reason I had to do that was because there are no instructions in this architecture for load relative. Okay, so for example, I cannot do the following in the Brookshear architecture. Load register something with the contents of the memory address whose address is stored in register something else. Right? There is no such instruction. I have to either know the memory address ahead of time or load it immediate. Right? So that third option of load relative just doesn't exist in this architecture. And so the self-modifying code is how I hacked it to get it to work. Okay, now, the good news is any real assembly language does have a load relative. Okay, but Brookshear is sort of a fake one for teaching purposes. So that's why I had to go through that rigmarole in that particular one. The two Brookshear programs that I asked you guys to write is the first one was something that just counts up to the whichever triangular number that's specified. So what is a triangular number, by the way? Do you guys happen to remember this from math? Okay, well, so what's 1 is a triangular number. 3 is the next one. Now, how do I get 3? 1 plus 2. So draw dots and you'll see, oh, that's a triangle. Okay, what's the next one? 6. 1 plus 2 plus 3. Okay, so 1 plus 2 plus 3 plus 4, that's a new one. 1 plus 2 plus 3 plus 4 plus 5, that's another one, and so on. Okay, so the program you guys are going to write, the first one, is, I do not know why that keeps happening. That's getting really annoying. The program that you guys are going to write is to basically take in an input from a memory cell. I think I said FE, and I just picked something kind of from thin air. And then, so like, let's say that you load in 6. Well, then you're going to count up 1 plus 2 plus 3 plus 4 plus 5 plus 6. Get whatever you get, and then dump that value out into memory. Okay, does that make sense? Yeah. So it's a loop, right, obviously. But it's a loop where you're not necessarily going to do it. You don't know how many times you're going to do it until you've loaded in the value from memory to see. Okay. And I think in the assignment file I wrote what it would look like in C or Java, right? The high-level code. Yeah. Okay. And then what's the other one that I asked you guys to do? Oh, that was the harder one. Then the other one was to check whether numbers are odd or even. So how did we check whether number was positive or negative, an integer? You check the far left bit, right? So the most significant bit is, if it's a 1, that means the number's negative. If it's a 0, that means it's not. How do you tell if the number is 0 itself? If it's literally all zeros, okay? So what are you going to use to extract a bit out? What was the trick for that? Okay, we called it masking, right? And you're either anding it, well, for that example, anding it against the bit pattern that you chose in the first place, okay? So what's the bit pattern to check if things are positive or negative? 1 followed by all zeros, which is what in hex? So 1 on the far left followed by 7 zeros is what in hexadecimal? 80. Okay, if you want to check if something's odd or even, you're checking the far right bit instead, right? The thing in the ones place. So what's the bit pattern that you're going to use in that case? All zeros followed by a 1 at the end. So 7 zeros and then an eighth 1. What's that in hex? 01. Okay. Gucci? Yeah? We good? You guys probably need coffee. All right, some of you have coffee. Yeah? Sure.
So how do you extract the rightmost digit again?
So what you would do is you'd have to say, let's load some register, I don't know which one, with the number 01. And then let's say that we load 2 with something from memory. Okay, then if we do a logical AND between registers 1 and 2, then what's going to happen? So if, let me write out, like, let me just pick a number out of at random. Okay, what's a good number? 10. Okay, so what is 10 in hexadecimal? Or sorry, in binary, right? 10 would be 0, 0, 0, 0, followed by 0, 1. No, you need 1, an 8, a 0, a 2, and that. Okay. And so that number is the number 10. Okay. Not 1 0 in hex, just literally the number 10, as in how many fingers we all have. Okay. What's the bit pattern with that is 1, right? And if I logically AND these, then the logical operations happen bitwise. Okay, so the far left bits are both 0. What's 0 and 0? And, not, yeah. So it'd be zeros in all of those positions, and what's it going to be in the final position? Huh? Because I'm doing logical AND, okay? So under what circumstances does logical AND output a 1? Only if both inputs are a 1. In this case, we don't have that, so it's a 0. This, by the way, is something I dislike about the way we say this stuff in English, because if I say 1 and 0 and I ask a fifth grader that, what are they going to tell me? 1, because we use the word and in common speech to mean addition, but I don't mean that here, right? I mean literally logical and. Okay, so in this case, the result of the logical AND was all zeros. What does that tell me about the number I started with, the number 10? It tells me that that's even. Okay, now we as humans knew that going into this, because we're not idiots, right? But this gives you a basis for the machine to decide whether or not the number is odd or even based on what bit pattern you get after doing this operation, right? Because what bit patterns could you get here as the result? You're either going to get all zeros, which indicates that the number is even, or you're going to get the number or the bit pattern 000, 7 zeros and then a 1 at the end. And then what does that indicate? That your number's odd. Okay. But it splits things into a Boolean choice, right? The thing you get, the bit pattern you get, is either all zeros or it's all 7 zeros followed by a 1. That's the basis for a jump command, and that's obviously, this is what makes a computer not a calculator, is that it can make those decisions. Okay, Gucci? Yeah? Okay, other questions? I'm sorry?
What does this assignment do?
The odd even one tonight, but assignment due dates are meaningless, right? Because, well, yeah, because existence is meaningless. No. Yeah, I actually watched a movie Sunday night. So, do we have any sophomores in the class? Yeah, that's right. Okay. So, Ghost in the Shell from EQ, what'd you guys think of it?
I loved it.
Okay.
Well, I liked it a lot, but then it kind of got boring in the middle, and I kind of spaced out.
All right, Noah, what'd you think?
Overall, it's a pretty good movie. Some parts kind of hard to keep up on.
Right? Was it like your mind was blown after it, like you didn't even know what to think? Yeah. Well, apparently I mean, you two had me for EQ, and since I was the one that picked that movie, then you sort of had an advantage. It didn't go so great for the other sections. So it's been suggested that we replace it with something. Okay, yeah, I personally agree. But one of the things that somebody suggested was a Korean movie called The Doomsday Book. And it's actually a series of 3 shorter films sort of put together. Well, the middle one is about a robot that was purchased by a Buddhist monastery to, perform services around the monastery, and ends up becoming this robot ends up becoming Buddhist himself, and like finds nirvana. And yeah, it was really interesting. The first and the third parts of the movie were terrible, so I wouldn't recommend wasting your time. It's an hour and a half of my life I will never get back. Anyway, um, that is also one of the contenders, and I haven't watched it yet. So yeah. Um, okay, so Jack asked, the max number is 2 to the 8th minus 1. What happens if you input a bigger number than a max number? Well, you can't, right? So for the one that loops, or the odd even thing, right? What are the numbers that you have to input here? You can only input an 8-bit number, which means as an unsigned integer, what's the range of values that can be? 0 up through 255, right? 2 to the 8th minus 1. As a signed integer, what are the values? They go from negative 128 all the way up through 127, okay? And it only goes up to 127 because, of course, 0 was in the middle somewhere there, right? Okay, so you literally cannot do that, or cannot use numbers bigger than this, because the width of the registers on this machine is limited to 8 bits, okay? Um, Now, what would happen if you asked the program for like the 400th, or well, you couldn't do 400. Let's say you asked it for the 100th triangular number. Okay, what's going to happen if you start adding 1 plus 2 plus 3 plus 4 plus dot 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 all the way up to 100? You're going to exceed 255, and when you do so, what happens? It's going to overflow and it'll wrap back around to 0. Okay, So yeah, so if you pick, I think in this I said, for testing purposes, just pick a number between 0 and 10, or 1 and 10, really, right? Um, for the which triangular number to generate, because triangular number 10 is what? 55. Well, 55 in decimal, and then whatever that is in hex, which is not going to be too big for the machine to express. Okay, so I just picked the number 10 there for, well, we got to stop somewhere, right? Uh, the purpose of this assignment was not to really worry too much about overflow. Believe me, we'll deal with that in spades later. Okay. Yeah, Gucci? Yeah. All right. So, no, I mean, I was joking when I said deadlines are meaningless, but really, like, when are things due ultimately? Right, before finals, right? So the deadlines I'm putting these things on Canvas are guidance deadlines, not firm deadlines. This is my attempt to COVID proof the semester.
Just for your class.
Just for me. Yeah, you're on your own with your other professors, bro. Okay. Now, that said, I'm going to be really irritated if in October you're like, Dr. C, how do I check if a number's odd or even in Brookshear again? Because I've got this assignment. Right. Please don't do that to me. Don't let the assignments stack up on you. Okay. So think of the deadlines on Canvas for this class as extremely firm suggestions. Okay. Looking at you, Walter, because I know what's going to happen. You're going to procrastinate. No comment. Yeah. Well, because believe me, I will bug you guys. I mean, there's only 14 of you, 13 in the room plus Jack, and I got a 2x4 in my office. So, yeah. Okay. So, anything else on the Brookshear Brookshear questions? And if you come up with more, just let me know. This stuff isn't rocket science. All right. So let me switch over then to the Pi, and let's actually take here my example C file, and let me save this first. There, so that we don't lose it. Okay, so let's just take, for sake of example, the assembly file that we produced from this. Actually, let me change it to that. To this. Okay, so we had a silly program that just added two integers, loaded in two integers, add them, and then returned that value. Okay, out. Great. Nothing particularly special about that program. But what I'd like to look at is a couple of cool things we can do with it. Let me get my notes pulled up here. So I want files, documents. Okay. All right. So what I'm going to do is I'm going to show you guys how to do a couple of things on here, and don't worry too much about the scribbling down the commands, because of course you can always look at this later. Okay, so I'm going to go into a terminal, and let me find where I put where did I put these files? Maybe they're in programming. There they are. Okay, so here's all the here are all the files for that example, right? And what I can do is I can look at, Nano is just a console text viewer. I could open this stuff up in Genie again, but if I open up my C file, right, that's the program that we were dealing with, same thing. And if I open up the source, or sorry, the assembly that was produced, okay, there it is, great. Okay, wonderful. Well, what I want to do is I want to talk about how to uh, use a debugger program called GNU Debugger to kind of do what the Brookshear emulator does. Okay, and by that I mean when I load something in the Brookshear emulator, right, I can step the execution one instruction at a time, and I can physically see exactly what's going on with all the registers, and in this case, because there's not that much memory, I can see the contents of every single memory cell and kind of watch the program execute step by step. Okay, so how do I do that with a real program? Well, what I first have to do is I have to assemble it, okay? And so in this case, I'm going to do assemble, so AS stands for assembler, okay? And then I'm going to give it a flag -G for debugging. And then what assembly file do I want to deal with? I want to deal with the assembly file example1.s. Where am I going to output the assembled object file? I'm going to output it to example1.o for object. Okay, so this is the object file is basically a binary thing. It's not quite executable yet. There'll be one more step, but we'll deal that with the second. Okay, so the -G is going to basically insert debugging stuff all over the place to yeah, okay. All right, so I run that. Okay, it doesn't look like anything happened, but it did. Right. Okay, and then I'm going to link this using GCC again. Oop, not main.o, sorry. Okay, and that's going to, oops, it would help if I could type today. That's going to take this object file and link it to libraries within the computer. Okay, so like the C standard library for like printing or taking string input, things like that. In this case, we didn't need to do that, but or because we're not using any libraries, but um, in the future we certainly will. Okay, and again, the -G does debugging stuff. Okay, and then what I'm going to do is I could run the program, which was example one, like so. Okay, and then it executed. It doesn't look like anything happened. Okay, because I didn't print anything or save any data, right? But it executes, great. Okay, but that's not really all that satisfying, right? It executed, but how can we watch it execute line by line? Well, enter the GNU Debugger. Okay, so GDB stands for GNU Debugger. And what file do I want to run? I want to run example1. Okay, so you load it, and this is what you're going to see. If I type list, that is not the one that I wanted. I'm sorry, guys. Hang on one second. Let me quit this. Crap. I wanted, because this is listing the C, not the assembly. Okay, I think I've messed something up here. go back to nope, and that's on an executable. Damn it. Okay, how did I manage to mess this up already? I just did this the other day. Okay, I've managed to mess this up. Let me go back up to what I was doing this weekend just to make sure I'm not forgetting some step. Oh, I know why. I know why. It's because I originally wrote this in C to begin with, that it's doing that. The other example I did this with, let me actually go to a different project and do this again. So projects, where did I put this file? Programming. Okay, here's where I was doing it. Okay, so I wrote this other file, so let me just show you what it, oops. Okay, so I wrote this other program that doesn't do anything particularly special, but I wrote this in assembly to begin with, not in C to begin with. Okay, so the that's the problem, is that if you write it in C, then the debugger is going to load the C, not the assembly. Okay, so I've got here a bunch of commands that do stuff. Okay, basically what this program is going to do is it's going to take the number 3 and 1, pass them to this function called chocolate twice. Okay, chocolate adds the two numbers together. Okay, so there's nothing special about that. And then it's going to multiply the results. So in the end, this thing's going to output 16 because it's going to add 3 and 1 and get 4. It's going to add 3 and 1 again and still get 4. And then 4 times 4 is 16 last time I checked. Okay, so for our purposes, who cares what exactly all these commands are doing right this instant? But how do I kind of step through the execution? All right, so let me quit this. And then I've already run these instructions that I just said to do. Okay, so then what I would want to do is I called this one Choco for chocolate. Okay, and if I hit list, right, it's going to start listing out my source assembly. Okay, now in my program, you'll notice that I've called the main program the routine called main. Okay. And I have to do that if I'm using GCC, because in C, your main function has to be called main. You can have other functions, but the big one, the ultimate everything is contained within, has to be called main. It's not a bad habit to be in. Okay, but anyway, so I've got a bunch of stuff there, and main is a label that starts here and then has a bunch of commands that happen after it. Okay, great. So what I'm going to do is I'm going to type break, oops, main. And that's going to put a breakpoint in the file, okay, at line 9 in this case, but that's really kind of the first line of the actual program because it's just data up above it. Okay, and then by putting in a breakpoint, what I can do is step the execution one instruction at a time, and we can watch exactly what's happening to all the registers. Okay, so what's the very first instruction in this case? We know what it is because I can scroll up and see it. Okay, it's this store pair something or other. Okay, but if I type step, oops, okay, first I run it and then I say step, or after I've put in the breakpoint, it hits the breakpoint. It says, okay, the first instruction is store pair x19, x30, stack pointer, blah, blah, blah. Okay. If I step again, then I can see the result of that execution. So I can also say this, and in fact, let me full screen the terminal here so it's easier to see. Okay. If I type info registers, it will show me what is the contents of all of the registers as I begin running this program. Okay. Now, a lot of them are, okay, so what are my registers? I've got 0 up through 22, and then there's more of them. It just can't fit it all on one screen. Okay, what are the contents of these things? Well, what does it look like? A bunch of gobbledygook at the moment. Okay. Okay, fine. And then the two columns, what's kind of nice here is this is what it is in hex, and this is what it's decoding to as a signed integer. Okay, so for example, all F's is -1 in 2's complement. Okay, that's useful for debugging purposes. Okay, now right now, there's nothing special in any of the registers, but there are a couple registers I want to point out. Okay, so notice a bunch of them have zeros in it. Some of them have numbers that just seem sort of random. There are a couple of special registers on this architecture. Okay, one of them is called the stack pointer, and we'll talk a lot about that. The other one is called the program counter. Well, we've seen the program counter, right? That's something that exists in the Brookshear architecture. What does the program counter do? In the Brookshear architecture? Yeah, what memory cell you're going to be loading the next instruction from to execute, right? So it's a pointer to where you're doing stuff from, right? To where you're loading data from for program execution. Okay, so the program counter is kind of an important thing for us. Okay, and then the stack pointer, like I said, we'll talk about what that thing means later. Um, there are also some special registers here. The CPSR, FPSR, and FPCR. Basically, these are status registers, or sometimes they're called flag registers. The Brookshear processor doesn't have one of these, but most real processors do for basically keeping track of, did overflow just happen? Is the number you just loaded in negative? Is it 0? And a few other things, okay? Those are useful for conditional expressions. And so when we get to things where we have conditional expressions, we'll talk more about the processor status register. And then the two at the bottom that have all zeros in them are things for the floating point units, which we're not using, so nothing's going on there. Okay, we will use floating point later, but right now everything's integers, so we don't have to worry about the floating point stuff. Okay, but if I step, what's the next instruction? Okay, what's this going to do? It's going to take the number 3 and stick it into a register. Okay, well, what's in register 0? Not the number 3. Okay, when will it have the number 3? After I execute that. Okay, so step is going to execute the previous instruction and tell me that this is the next instruction, but it hasn't executed it yet. Okay, now if I do info registers, what's in register 0? 3. Okay, great. Now let me step one more time. Okay, the next instruction is to store pair, okay, whatever. But what should I expect to see in register 0 and 1 now? What should be in register 0? 3. What should I expect to see in register 1? 1, because that's what I told it to load in, and sure enough, look what we got. Okay, so we can actually see that yes, in fact, the registers are being loaded with the numbers that I thought they should be loaded with. Okay, and if we continued program execution, we could kind of keep track of, oh, yeah, the numbers are going where I'm expecting them to go. And if we were like trying to debug a program and we found the exact step where things looked a little weird from what they should be, then we'd be like, oh, okay, well, there's the problem. Fix that. Okay, good. Okay, so yeah, this GNU Debugger program is kind of handy for a lot of things. And I should say that, so I bought a print copy of the manual. I think I put a link to the PDF on Canvas. It's an open source thing, so the manual is free. And if you want a print copy, it's like basically the cost of photocopying it. It's like this thick, right? So, and Jack, since you can't see my fingers, it's like 5 or 6 centimeters thick. I mean, it's a pretty big manual. So we're just barely scratching the surface of the sort of stuff that this thing can do. Okay, but you know, we've got this, and it's kind of handy. Okay, good. All right, so that is just sort of a quick crash course, if you'll pardon the pun, into the GNU Debugger. Okay, the other thing I wanted to show you guys is, so when we wrote our example, well, I closed the file, of course. When we wrote our sort of example Brookshear program, just this silly one, right? Up at the top there, notice what I've got. I've got my memory addresses going down the side. I've got the instructions in their machine code equivalent. Then I've got the assembly that is the human readable stuff. Okay, how can I produce this type thing for an ARM assembly file? Okay, so how could I take, for example, this assembly file that I wrote and spit out something that looks like that example that I had a minute ago? Okay, doing so is called generating a listing file. Okay, and here's how you do that. Okay, so let me quit the debugger, go back to the terminal. Okay, so what I'm going to do is I'm going to take, I'm going to assemble, but then I'm going to put -a, and what thing do I want to assemble? Chaco.asm, and then I'm going to put a greater than symbol, and I'm going to do chaco.lst. Okay, so let me actually remove this part and just run that as is. Okay, what that does is it spits out this stuff to the console. Okay, so do you guys see, this is basically like what we had with our Brookshear example. We have it spitting out line numbers, memory addresses, machine code, and then assembly all together. But it's just dumping this data into the console. Wouldn't it be nice if I could save that to a file? Yeah? Okay, so here's how you save it to a file. What I'm going to do is, oops, I'm going to use what's called a pipe, okay? And the greater than symbol, when you use it in the terminal like this, means take the output from that program, okay, whatever it's dumping, and write it to a file called chaco.lst, LST for listing, okay? And when I do that, it has produced a file that has all of the stuff we were just looking at, but now I can load that file and read it later. It's not ephemeral, it just got dumped to the console. Yeah. Yes. Yes, because the assembler doesn't care what the extension is. right? The assembler just cares what is inside the file. And so, yes, here it's a .asm because I hand wrote this assembly. But if we had done this for the other example where we had the machine produce the assembly, it would do the same thing. Okay, and what it would output is, let me load it. Okay, what it's going to output. So here I'm just loading it in the sort of console text editor Nano. I could open this up in Genie or any other text editing kind of application. So what do we see there? Well, up at the top, we've got the data. Okay, so that section of it has, in this case, all of the stuff you see there in hex is the fact that I've got a string and it's storing that string in ASCII. And then how do I know that the string is ended? I need to have the null terminator at the end of it. Okay, so that's the 0, 0 down at the bottom there. It's putting all this red stuff in just to kind of, make it clear what's what. And then I've got my main program, my actual code, okay, which is what's listed down the side there. The far left is line number, okay. I didn't put that in with the Brookshear code that we had, but we certainly could have done line numbering if we wanted. What's to the right of that? Okay, so we've got line number. So this whole thing starts on line 9, okay? And then we see 4 zeros. What does that mean?
Register 0.
Nope. Okay, it's the memory addresses. Okay, now it may seem funny. Why is that all zeros here? Because this program is not going to be stored at memory cell 0, right? When it gets loaded, it's going to be loaded into some other memory address. So when the memory addresses, right, are going to be relative. So let's say that I put it in memory cell 200,000. I'm just making up a number, right? Really, these things are relative to the program itself. So the program starts somewhere, and this 0000 is relative to that start value. I don't know where that start value is because the operating system determines that, right? It's going to choose where to put this thing in memory for me. Now, if we were doing this on an old-fashioned machine like the 8-bit Nintendo, I could decide where to put my initial instruction. Okay, and specify that. But here I don't have that flexibility because the OS is going to sort of manage things for me. So all of that, like I said, is relative in this case. How are these things increasing? So what's the step count it looks like between instructions? How many cells does it, or memory cells does it take to store an instruction here? Huh? 4 how many's? 4 whats? 4 bits, 4 bytes, 4 nanobuckets? It's 4 bytes, okay, corresponding to how many bits? I know it's too early in the morning to do multiplication of 4 and 8, but what do we get when we do so? 32, right. So one of the nice things about the ARM architecture, similar to the Brookshear architecture, how much data was required for every single instruction in Brookshear's architecture? Each instruction took exactly how many bytes? 2. Okay, great. It was a relatively limited architecture, but everything took precisely 2. How many bytes does every instruction take in the 64-bit ARM instruction set? Precisely 4 bytes. Okay, so 32 bits. Now you might say, wait a minute, I thought it was a 64-bit architecture. Okay, well, what does 64-bit architecture mean? It means how wide are the registers, not how much space does an instruction take up. Okay, so this is a 32-bit or sorry, it's a 64-bit architecture, but each instruction only takes up precisely 32 bits. And every instruction takes up exactly 32 bits. Okay, that's nice, right? There are other architectures where that's not true. Okay, so for example, the 8-bit Nintendo architecture, not all instructions take up the same amount of memory. Some are longer, some are shorter, which is both nice and annoying. Okay, there is sort of a utility though in these all being the same thing. All right, now, what's in the column after the memory addresses? Okay, so the stuff that 8 characters in hexadecimal. So all of this stuff right here. This stuff is what? It's the actual machine instruction. Okay, now unlike the Brookshear, where it was really easy to look at the instruction and decode it in your head, can we decode that in our head? Probably not. Okay, and decoding the machine code instructions on this architecture is a little bit more annoying than with Brookshear. Okay, we could do it, and we'll talk about that a little bit more, but it's not obvious just looking at it what bits are what. Now, you can sort of look and say, well, all right, I've got 2 store pair instructions, right? So look at lines 9 and 12. These are both doing similar things. They're both doing whatever STP means. What's similar about the stuff here and what's different about them? Well, they both have BFA9 at the end. So maybe something's going on there, right? But then the other parts are different. Okay, so it's not necessarily obvious what's so special about BFA9 or whatever, right? But yeah, and I'll show you guys, I've got a manual, actually a really handy Excel spreadsheet that somebody made of bit by bit exactly how to decode all of these instructions. Okay, okay, so that's a listing file, and if I just kind of scroll down here, right, it's just kind of more of the same. I've got, you know, my function called chocolate, and then these defined symbols, that's stuff that got defined by the assembler and the debugger. Undefined symbols, printf. Well, I didn't have to define printf because the C standard library defines it for me, and I just link to that. Okay, but in terms of my own program, it's not specified, okay, yet. Okay, and yeah, then this X and D, and you know, those are some other things. Okay, so what we're going to start really with on Thursday is starting the glorious process of writing things in this ARM assembly language from scratch, okay? And looking at, well, I have some data up at the top, I've got this text section, I've got this function called main, right? There are different chunks to my assembly file. What are all those chunks? What needs to go where, other than obviously the code goes in the code part, right? Where else would it go? And what are kind of the basic instructions that we'll use to get started? I mean, it'll be a lot of the stuff like moving data around and doing addition and kind of silly things like that. But then we'll build this up to stuff like, well, let's think back to when you guys took CS111. Did you guys do something like a program like the following where you say took a number in as input and then output a string that had those digits as its thing? Or you could kind of go the reverse direction, take in a string that has a sequence of numbers and make an integer that has that same value, right? So like, let's say you took in the string 1, 2, 3, 4, then generate a number like an integer 1, 2, 3, 4, right? That sort of thing, right? So string processing, we can do that. We'll talk about floating point eventually. Hopefully we'll also get to talk about some of the advanced instructions, which are called SIMD, single instruction, multiple data. recursion, you know, all this sort of stuff. Okay. All right, so that's a crash course on the GNU Debugger and listings, and we'll be using this as we write example programs to kind of see exactly how they're executing. Okay, Jack, sorry, I just saw your question. The -O means it's going to output to whatever is written after the -O. So it's just telling it where to output something. Okay, I'll quit the stream here and see you guys later.